Having seen what a continuous function is for the case of complex functions, now it is time to learn about differentiating a complex function. Again, we will appeal to the definition of derivative in the case of a real function to understand and generalize that notion, that concept of derivative to the case of complex functions. For a real function f of x, which we had chosen to represent earlier using a curve earlier, derivative of a function was defined as it is a limit epsilon tends to 0 of the difference of its value at x plus epsilon with its value at x divided by epsilon. So, in the limit when epsilon tends to 0, this ratio, which sort of gives us the rate of change of f of x as you move from x to x plus epsilon, defines the derivative of that function. If such a derivative uniquely exists at a certain point x, then we say that f of x is differentiable at x. It is good to note that it has a certain geometric meaning in the case of a real function, which gives us the slope of a tangent vector to that curve at point x that we can draw. To define what a derivative for a complex function at point z is, let us look at any arbitrary point in the neighborhood, the close neighborhood of the point z, such that its coordinates are, or its it is such that it is a point represented with z plus h. It is a complex number represented with z plus h. Then the derivative of f of z at z with respect to z is defined as the limit h tends to 0 of the difference of f at z plus h with f at z over h. One could observe the close similarity for the definition of derivative of f of z with that of df by dx. The only difference that we demand is that the point z here, for which we are defining the derivative, is now defined as a difference of f of z and f of z plus h, where z plus h could be any point in the close neighborhood of z, such that this notion of derivative, this definition of derivative I have defined, does not again depend on which direction z plus h is as you move from z. Okay. So, the point z plus h defined here could be any of the points in the close neighborhood of the point z, such that this definition of derivative does not depend on which direction you approach the point z, and thus ensuring that the derivative has the same value at the point z, irrespective of the approach to the z. If such a derivative exists for a function, we call such a function a differentiable function to be a differentiable function at z, a function to be differentiable at z. This particular condition, that the derivative should have a unique value as you approach from different direction, has a certain implication, certain consequence. That consequence can be seen if we look at the notion of derivative in terms of the real and imaginary part x and y. So, let us look at the definition of derivative for a function. Let us choose that function to be u of x comma y plus I into v of x comma y in its most general form. So, let us consider the point z again, which has the coordinates x plus y, that is the point z, and look at the derivative of f at the point z as you approach the point by moving in such a way that only the real variable changes by keeping the imaginary variable y constant, and see what its value is. If I suppose move only along a direction which is parallel to the real axis, then it is clear that only my real variable would change. Say if I look at another point which is obtained by moving from z by along a direction that is parallel to the real axis, then such a point would have a real part which is different from that of z, while its imaginary part would remain the same. So, let us call that point x plus delta x and y. The value of function at that point would be let us call that point f at x plus delta x comma y, and its value would be u at x plus delta x comma y plus I into v at x plus delta x comma y. Now, we can use the definition of derivative by considering these 2 points and taking the limit delta x to 0. If I do that, as per our definition of differentiable function, if the function were differentiable, I should get a certain derivative at the point z. So, let us consider that. If I take f at x plus delta x comma y, which is this point, and find its difference with the point with f at the point x comma y, and divide it with the difference between the 2 points, which is delta x, and take the limit delta x tends to 0, I should have got the derivative of f at the point z. Let us see what this condition would result when we use this form of u. Writing it in terms of u and v, observe that when I consider this difference, it gives me u at x plus delta x comma y minus the real part of f at x comma y, which is u at x comma y, plus the difference of the imaginary part of f at x plus delta x comma y, which is v at x plus delta x comma y minus v at x comma y we get df by dz out to be, substituting this form for these two terms, we get u at x plus delta x comma y minus u at x comma y divided by delta x in the limit delta x tends to 0 plus I into v at x plus delta x comma y minus v at x comma y over delta x in the limit again in the limit again where delta x is taken to 0. Now, observe that this particular quantity, which is the change in a particular function u, which is a function of two variables x and y, as I change only one of the variables keeping the other constant, the rate of that change is the definition of the partial derivative of that function with respect to x. So, that term is really the partial derivative of u with respect to x. Similarly, this term should give us the partial derivative of v with respect to x. So, which tells us that as I approach or as I find the derivative by approaching the point z by taking the limit delta x tends to 0 from a neighboring point with coordinates x plus delta x and y, the definition of derivative must be equal to partial derivative of u with respect to x plus I times the partial derivative of v with respect to x. Now, let us find the definition of derivative or apply the definition of derivative as I approach the point z from a perpendicular direction in which the real part of the z remains constant while the imaginary part changes. So, to do that, I choose a point which has its real part the same as z while its imaginary part differs from that at z by a quantity delta y. If I do that, again the definition of derivative can be written again as a limit of now y, the quantity delta y tending to 0 of f at x comma y plus delta y minus f at x comma y over delta y. We could again express f at x comma of this I times delta y coming, because we are taking, while taking the limit, it is only the imaginary part of z that varies. Again we could use the form of f in terms of u and v and express this whole quantity as u at x comma y plus delta y minus u at x comma y over I times delta y plus I times v at x comma x plus y plus delta y minus v at x comma y over I delta y in the limit where delta y tends to 0. As you could easily observe, this term is now proportional to 1 over I times the partial derivative of u with respect to y, because in that process of taking the limit, only the y variable changes, keeping x constant. So that the last line gives us 1 over I, which is nothing but minus I of partial derivative of u with respect to y as the first term, and next term the factor of I cancels in the numerator and denominator, leaving us with partial derivative of v with respect to y. So that is the form or the value of derivative of f that we get at point z as I approach the point from above purely along the imaginary axis. Now, if the function is really differentiable, both these definitions should give me the same value of the derivative, which means that the derivative that I obtained in the first method by approaching along the real axis, real direction, should give me the same number as the derivative that I got by approaching in a direction that is parallel to the imaginary direction. That means I should equate these two expressions for the derivative of f with respect to z, which gives me the condition equating the real parts. I find del u by del x to be equal to del v by del y, while equating the imaginary parts I get del v by del u by del y to be equal to minus of del v by del x. So, now we have learnt that in terms of the Cartesian variables, the condition of a function being differentiable translates into two conditions, that the partial derivative of u with respect to x must be equal to the partial derivative of v, the imaginary part of the function, with respect to y, the imaginary variable. Second, the partial derivative of u with respect to y must be equal to minus of partial derivative of v with respect to x. If these two conditions are satisfied, then we can say that that function has a unique derivative at the point z. These conditions go under the name Cauchy Riemann conditions. And the functions that obey these conditions are very often called analytic functions. That is, if a function obeys Cauchy Riemann condition at a certain point z, then we say that the function is analytic at that point z. Okay, having seen the Cauchy Riemann conditions, that is a basic requirement for analytic functions to satisfy. Let us write those conditions in complex coordinates. The conditions as stated in the real and imaginary coordinates, the Cartesian coordinates, were of the form and del u by del y equal to minus del v by del x for a function that satisfies, so for a function of the form now it is good to write the same conditions in coordinates z, z bar. To do that, let us write each of these derivatives first. Del u, starting with the derivative del u by del x in coordinates z and z bar. So, that is done by observing that a partial derivative with respect to x involves a change in z as well as a change in z bar. And the change that comes through z will have the form del u by del z into del z by del x, and the change that comes through the change in z bar is taken care similarly by a term del u by del z bar into del z bar by del x. Well, since z has been chosen to be x plus I y from the beginning, del z by del x gives us identity, and z bar being x minus I y, del z bar by del x is also identity, giving us del u by del z, which I will write in short as del z u times 1 into plus del u by del z bar into 1, where del u by del z bar will be written in a shorter notation as del z bar into u. So, that is what del u by del x looks like in complex coordinates. Similarly, you can write del u by del y as well in the same set of coordinates, which will take the form clearly del u by del z into del z by del y. Del z by del y gives me I, and plus del u by del z bar into del z bar by del y. Del z bar by del y gives me minus I to del u by del z bar. That overall gives me I into del z u minus del z bar. Okay. Now, it is clear that the derivatives of v with respect to x and y will have similar forms, where we only have to replace u with the function v. So, writing both these in the respective form and expressing the Cauchy Riemann conditions, we get del z u plus del z bar u equal to del v by del y, which can be obtained by replacing u with v in this expression, and that has a form I into del z v minus del z bar. The next condition similarly involves del u by del y, which is computed here, I into del z u minus del z bar u, and the right hand side of that gives me minus of del v by del x, which has the form let us multiply the second equation with I. And then add that to the first equation. When I multiply the second equation with I, on the left hand side you get I square outside the term, that is minus 1, and when I add that to the first term, the term which involves partial derivative of u with respect to z, it appears with opposite signs and they cancel. On the other hand, the term that involves partial derivative with respect to z bar adds up because they come with the same sign, giving us on the left hand side 2 times del z bar u. On the right hand side, we get multiplied with I, you get a term involving minus I as a coefficient of the derivative with respect to z, partial derivative with respect to z, which has opposite sign, which appears with opposite sign in the first equation. So, when we add, that first term cancels and we are left with just the second term, which adds up to give minus 2I del z bar v. Bringing this term to the left hand side and cancelling away the factors of 2 on either side, we get del z bar u plus I v equal to 0. which in fact tells us that if I may write f, the function whose real and imaginary parts are u and v, as f of z comma z bar, for it to obey the Cauchy Riemann conditions, it must satisfy the partial derivative with respect to z bar vanishing. So, it must satisfy the condition that the partial derivative of z bar must vanish. So, we can say that this is the form of one of the Cauchy Riemann conditions when we express it in complex coordinates. It is important to observe what the meaning of such an equation would be. Now, when we take a function of z and z bar, if the partial derivative of that with respect to z bar has to vanish, then it is necessary that f be only a function of z and should not be depending on z bar. That is the only way a partial derivative can be assured to vanish. So, this tells us that if a function obeys Cauchy Riemann condition, which is necessary for it to be analytic, that function has to be a function only of z. Now, it might look as if this particular variable z out of the two variables z and z bar has got a special treatment in this, in that the definition of analytic function involves only z here. There is nothing so special about it that can be checked by observing back the two equations and noticing that if instead of multiplying with I had multiplied with minus I, we would have got the minus I and carried out the same operation of adding the two equations after multiplication with minus I. We would have got the equation del z u into twice del z u twice del z u on the left hand side, while on the right hand side we would have got minus 2I del z v, which would have resulted in an equation del z of f z z bar equal to 0. Now, that could happen only if the function were not a function of z, but only of z bar. If that were the case, then I would have had to write it as f of z bar by replacing z with z bar in there. But of course, if I replace z with z bar, I would be getting the function as u minus I v, which is what really f here is if you observe this equation. By taking this term to the left hand side, what you get there is u minus I v under the action of partial derivative with respect to z. Okay. So, which indicates that certainly we are looking at complex conjugate of the function that we considered when we looked at f as a function of z. So, to distinguish these two parallel ways or two possible ways of defining an analytic function, usually this is called an analytic function, while this one is often called an anti-analytic function. Whatever we are going to say for analytic function holds equally well for anti-analytic cases as well, but it is good enough for us to stick to just one of them as a matter of convenience to understand the properties of analytic functions. So, this is what we will do from the next lecture onwards.